Hi everyone, I'm Farsana and today I will be presenting our research paper Hybrid Convolutional Neural Networks for PIMA Indians Diabetes Prediction. This paper explores developing and validating a hybrid classification model for assessing the risk of diabetes among the PIMA Indian population. Leveraging a comprehensive dataset that includes demographic information, genetic markers, lifestyle factors, and historical health records, our proposed hybrid CNNs employ advanced machine learning algorithms to classify the likelihood of diabetes onset. The research aims to contribute to early detection and prevention strategies, ultimately improving health outcomes within the PIMA Indian community. So, what is diabetes? Diabetes is a complicated chronic disease arising from disrupted metabolism. It's either due to insufficient insulin production, which is type 1 diabetes, or insulin resistance, which is type 2 diabetes. Elevated blood sugar leads to various complications like heart attacks, nerve damage, kidney failure, and stroke. Insulin produced by the pancreas regulates blood sugar by facilitating its absorption by cells and conversion into energy. Malfunction in insulin production leads to hyperglycemia, a condition where blood sugar levels are elevated beyond the normal threshold. So, what is the motivation behind this research? As I was saying, diabetes is a serious and growing health issue globally. According to WHO, about 422 million people worldwide have diabetes, the majority living in low and middle income countries, and 1.5 million deaths are directly attributed to diabetes each year. Both the number of cases and the prevalence of diabetes have been steadily increasing over the past few decades, particularly among the PIMA Indian population, who are known for a higher susceptibility to type 2 diabetes. But why do PIMA Indian population face such a disproportionate burden of type 2 diabetes? Experts say that it's influenced by genetic predisposition, environmental factors, and socio-economic challenges, which is why early prediction of diabetes is crucial as it can prevent severe complications. However, the lack of accessible and accurate predictive models makes identifying and intervening early challenging. Developing predictive models for early risk detection and targeted interventions is crucial for addressing this health disparity. This research aims to develop and validate a hybrid classification model to assess diabetes risk within this community. Let's go through some of the related work in this field. The use of machine learning techniques for predicting diabetes in the PIMA Indian population has been a focus of increasing interest in the scientific community. Several previous studies have investigated various approaches, highlighting methodologies, datasets, and outcomes. Here are a few of related work in the form of a timeline before you. There are neural network-based approach and e-diagnose system and intelligent hybrid systems developed before. Some of the past research has explored traditional ML methods like logistic regression, k-nearest neighbors, Gaussian naive Bayes, SVMs, decision trees, and neural network models. These studies have demonstrated various degrees of success in predicting diabetes, with some methods achieving higher accuracies than others. However, many of these methods have limitations, including overfitting and inadequate generalization of new data, which is why we have the following proposed methodology. The methodology involves primarily we have to collect the data, gathering a large data set containing genetic makeup, demographic characteristics, lifestyle factors, and medical history of PIMA Indians. Next is another crucial step, data pre-processing, which includes cleaning, normalizing, and handling missing values. This is essential to ensure data quality, and consistency. Next, we have hybrid CNN model development. We are aiming to build a hybrid model incorporating traditional ML models with a CNN architecture. Now, we can use this model to train on the prepared dataset and evaluate its performance. Now, let's discuss the model architecture. As you can see in the image or in the slide, the hybrid CNN model consists of multiple layers: the input layer, convolutional layers, dropout layer, pooling layer, flattened layer, and the fully connected layers. So, let's begin with the input layer. This layer takes in the raw data. In this case, a sequence of 9 values, and its shape is defined as none 9 1. The none represents a variable batch size, which means our model can handle inputs of variable lengths. Next is the convolutional layer. For this layer, we have used 2 convolutional layers. These layers apply learned filters to the input sequence for capturing local features. The first convolutional layer has a kernel size of 1. It means that it looks at one data point at a time and outputs a feature map of size none 764. Now this process is repeated by the second convolution layer. This will take in the output of the first convolution layer as the input to give an output of none 564. This is followed by a dropout layer. We all know that dropout is one of the best regularization techniques. This layer randomly sets a fraction of the activations to 0 during training. This helps us to prevent overfitting. Now this layer helps the model generalize better on unseen data by introducing noise and forcing it to rely less on specific neurons. This is followed by the max pooling layer. Max pooling layer is the layer which downsamples the feature map by taking the maximum value within the window. Here, as you can see, it reduces the spatial dimension from none 564 to none 264. Effectively extracts the most significant feature, thereby reducing the computational time. This is followed by the flattened layer. This transforms the 2D feature map into a 1D vector of size, here none 128. This prepares the data for fully connected layers. Now finally we have the dense layers, and for this model we have used 2 dense layers. They are the fully connected layers. The first dense layer has 100 neurons and it's act as a classifier. The final dense layer has 1 neuron. This one will predict the output value, which is 1 or 0 here, and that is diabetic or non-diabetic. So what is the advantage of the hybrid approach compared to the traditional models? We here exploit the advantage of the robustness of CNNs in feature extraction. The proposed model, it combines the strength of traditional machine learning architectures with the power of deep learning models. That means it has the best of the both worlds. So in summary, this 1D CNN uses a sequence of convolutional layers to extract the local features, then dropout layers to prevent overfitting, and max pooling layers to downsample the feature maps. The flattened feature vector is then fed into the dense layers for classification. Let's move on to the experimental setup. So after the data cleaning and process, we have the exploratory data analysis waiting. Here are some of the key findings from exploratory data analysis is that the PIMA Indians diabetes dataset comprises various medical predictor variables, which includes the number of pregnancies, BMI, insulin levels, etc. The target variable is the outcome variable. It represents the diabetic status, which is 1 for diabetic and 0 for non-diabetic. The dataset exhibits missing values, particularly in features like glucose, blood pressure, skin thickness, insulin, and BMI, which is not normal. That's why we impute these missing values using a combination of mean and median values based on the distribution of each feature. We can now perform correlation analysis, which reveals that glucose, BMI, and age are the most correlated with outcome. This suggests that they are very important in predicting diabetes. After the training and testing procedures, we can proceed on to the evaluation part of this. The evaluation metrics used to assess the effectiveness are accuracy, precision, recall, and F1 score. Next, we can compare the performance of the proposed model against the traditional machine learning models. So in the results, we have the traditional machine learning models like SVM, logistic regression, and Gaussian NB exhibiting the highest accuracy among all, which is ranging from 75 to 77%. While the proposed hybrid models also show significant improvements in diabetes prediction, achieving higher accuracies compared to most traditional models, as you can see here. For instance, the KNN classifier achieved a 7% increase in accuracy, while the hybrid CNN model with XGBoost, Decision Tree, AdaBoost, Random Forest, Light GVM, and CatBoost have also improved ranging from 1% to 4%. However, the hybrid approach with Gaussian NB, logistic regression, and SVM is not up to the mark. They have reduced in the performance, indicating that they are unsuitable for this hybrid model. So, from these results, what are the key takeaways of our approach? It's obviously the improved accuracy. Our hybrid CNN model demonstrates significant performance improvements in diabetes prediction compared to traditional machine learning models. Then comes the enhanced interpretability. We utilize model interpretability tools to gain insights into the influential factors driving predictions, enabling a deeper understanding of decision-making process. So, to conclude, we shall say that the proposed hybrid CNN model offers a promising approach for predicting diabetes in the PIMA Indian population, demonstrating notable improvements over traditional ML models. The method's interpretability and explainability contribute to building confidence among medical professionals and PIMA Indian community. The study highlights the importance of considering the unique characteristics of the PIMA Indian population when developing predictive models for diabetes. We have also made room for the potential directions for future research. So, the future research should focus on investigating the impact of other factors which is not captured in the current dataset, and we can employ additional data sources, collaborate with healthcare professionals to improve the model's effectiveness and accessibility. We shall also include a more diverse population, which will contribute to a more robust and generalizable diabetes prediction model. So overall, this research demonstrates the potential of hybrid CNN models for diabetes risk prediction among PIMA Indian population. Our findings highlight the importance of leveraging advanced ML techniques and combining them with domain expertise to achieve significant improvements in healthcare outcomes. By continuing to refine and develop our hybrid model, we aim to empower communities and healthcare professionals with powerful tools for early detection, intervention, and ultimately improved diabetes management. I would also like to extend my gratitude to my institute ICER Trivandrum for providing all the facilities that is needed for this research. I would also like to thank Dr. Alvin Poulose, my professor and mentor, for all the support and encouragement he has provided for conducting this research. Once again, by thanking everyone for your time and attention, I conclude my presentation before you. Thank you.